we are getting into the topic of electromagnetic induction. And so we're going to first go over some interesting behavior that occurs that relates to this. In the picture here, we have two solenoids that are next to each other. One's hooked up to a battery. And what happens is when the switch is flipped here, which allows this to be an open circuit, closed circuit now, what you may not know is this coil here can provide a sort of resistance that we're going to get into in the next chapter, but basically is a current starts to flow through here, and what happens is initially goes from 0 up to some value rather quickly. Again, it's sort of based on what the internal resistance everything is here. But if you place another coil next to it that is clearly not connected to this other circuit, you will read a momentary current in the coils here, in this whole thing. While this coil is sort of winding up, so to speak, this secondary coil here will show a little deflection in the ammeter. You can also do a similar thing with a bar magnet, placing a bar magnet through the coils of the solenoid here. As the magnet is pushed through or pulled out, there is a current that is detected in the coil here. Now, there's no battery here, right? That's one thing I want to be clear about. In both of the examples, there is no battery, but a current does flow in these two examples here. Depending on which way you push or pull the magnet, either in or out, depends on, will determine the kind of deflection that occurs in the needle, whether it's going to be a current going one direction or another direction. You can do another similar exercise where instead of inserting the magnet through the coil, you can simply take these coils and push them in or out of the magnetic field due to a setup like this you see here, and you see a deflection in the meter here showing there is a current. By the way, back in this example here, doesn't matter if I push or pull the magnet in or I actually take the coil and just do it with the coil. Put it, move it up, move it down. It's the same thing's going to happen here. Okay, so all of these behaviors are what we call electromagnetic induction, and ultimately what is happening here is the presence of the magnetic field that is generated by these things. There's a magnetic field generated by the magnets. There's a magnetic field generated by the coils. When that magnetic field undergoes a change, a current is induced in the vicinity of that magnetic field. And this is what we call electromagnetic induction. And we're going to spend a good chunk of this chapter investigating this phenomenon, how it happens and how it's useful for things. So to go through that, let's look at probably the simplest example we could generate of this. Now, the example that I'm going to show you here is a very simplified, very bare bones approach to this. This is our approach given the tools that we currently have in electricity and magnetism. After you see the phenomenon, and I try to convince you that this exists, we will then shift to a completely different system for explaining that phenomenon. Okay, so in the example here, we have some sort of, imagine we have some kind of conducting piece here. It can be some kind of long rectangular piece, and we have it in the presence of a magnetic field. This magnetic field goes into the page, and what happens is the conductor is pushed to the right. Okay, so it has some velocity to the right, and what that's going to do is it's gonna cause charges in the conductor to experience forces due to the magnetic field. So if you do your cross product stuff here, V is to the right. Open your palm into the page for the magnetic field. Your thumb points upward. Positive charges would go up. Of course, negative charges would go down. And as this thing is being pushed, if you can maintain this velocity here, you're going to generate a constant force that's going to cause charges to separate on the conductor here and create a separation of charge, which therefore creates an electric field inside the conductor. Now, you just heard me say electric field inside the conductor, and maybe that makes you open your eyes and say, wait a minute, there's no electric field inside conductors. Didn't we go over that before? And I would say we did, but the condition was electrostatics. When things don't move, that's true. When things do move, not true anymore. So, I mean, that was the whole reason, that's the whole thing about circuits, right? Is that's not true because it's not electrostatics, electrodynamics. So we get a separation of charge here. Positive builds on top, negative builds on the bottom, and we create a potential difference. Well, that will continue until the electric field produces a force that can balance the magnetic field. And so with a given velocity and strength of the magnetic field, we can actually speak of a potential difference that's being created here as a result of this motion. So let's put some numbers behind that. If this has a length L to it, okay, then you equate the forces. That would be QE. Do I have this thing hooked up? Maybe, yes, no. What if I do? If I draw this, does that work? No, it's not hooked up. Let's hook it up. It is hooked up. Crying out loud. Technology. What's going on here? So, going back here, we would equate the forces. So QE is the electric force and QVB is the magnetic force. The charges drop out here and we're left with the relationship that the electric field equals the velocity times the magnetic field. Now, if we identify that the electric field, can be written as change in potential, right? A voltage divided by some distance. I'll just call this S. Well, the distance here is this value L. That's the length of the conductor. So we can substitute that in, and we can solve this for the voltage, and we end up with this expression down here, VLB. And this is kind of strange, but it involves the velocity of the conductor, the length of the conductor, and the magnetic field that the conductor is placed in, and this tells us what the potential difference is. So it is a type of, you can refer to it as an EMF. You can refer to it as a voltage that can supply a current. And so what we did here, again, we created forces. We recognize that this electric field here is going to be delta V over delta S, where delta S is L. And we go from there, and that's it. So, question for you now. I got a lot of questions today. You're going to be sick of them. Metal bar moves through a magnetic field as shown. How the charge is going to look when this thing moves. So think about that for a moment. Well, most of you are saying B. There's a little bit of A. Well, let's see here. V is down. Right? V is down. B is out of the page, so the electric force will point to the left. It looks like it is B. It is B. So your magnetic force, I should say, points to the left. It would push the positive charges to the left, and obviously the negative charges would go to the right. So, great. Okay. Imagine we were to take this piece of metal here and say it is placed on a rail. Okay, so imagine that we have this wire here is shaped so that this conductor is basically in contact with the wire, but it's on a rail. This wire acts as a rail, and so we could push the conductor along the rail here, and that will cause the charges to separate. That effectively, that is a source of voltage, and because it's connected to the wire, it's going to induce a current. So that's the first time I've used that word, induce the current. The current has been created. The word induced is perfect. The induced current is created by the motion of the conductor here. If the velocity was 0, the current would be 0. We're simply using Ohm's law here to determine what the current will be. And so we just take our potential difference, divide it by the resistance being the sort of internal resistance of this wire. Or if you have a circuit element like a resistor or something, then that would be what R is here. But you have to have some resistance for the current to be there. But if the positive's up here and the negative's down here, that's going to cause charge to move. Well, current's going to move in a counterclockwise way. All right, now that's based on this particular setup here. Velocity is to the right, the magnetic field is into the page, causes positive charges to go up, negative go down, and because the closed loop is on the left-hand side, that's going to create for us a counterclockwise current. Now, the expressions that we have down here that represent the EMF and the current, those are going to be universally true in, for these kind of situations, but specifically about which direction the current goes, that's determined by you thinking about how the charges separate here and then thinking about it like it's a battery. Okay. So you can see here that, it was just the motion of the conductor. The fact that the conductor moves establishes this current, which seems pretty wild, right? Because we haven't been doing things like that. That's not how we've talked about sources of current. But this is now become a source of current here. Now, what will happen here, though, is you can't keep pushing that wire to the right. If you think about it, if that wire is moving to the right with some velocity, it can't maintain that velocity because that's just generating a current for free, right? Because think about what is changing, right? In energy conservation, if that thing moves at a constant speed to the right, that's not a change in kinetic energy, and so we can't just magically get electrical energy out of this. There has to be some input of energy to do this. Well, the current that gets created will now create a second force. And this second force is the force of the current, the force on the current because it's in the external field. So once the current starts flowing, and that's what's going to happen, the current's going to start moving up here, because again, positives up top, negatives in the bottom. And so if we do our right-handed rules, okay, your fingers go up for the current, your palm opens into the page, and your thumb extends to the left. And so there is a magnetic force that is exerted on the current simply due to the fact that you have generated the current in the conductor. So if I were to, just to be clear about this, if I were to just simply kick the conductor to the right and let it slide along the rail, it will initially have a speed, and then it will gradually slow down because this magnetic force is going to be present to do that. So in order to get this current to be constant, you're going to have to supply a push that equals this magnetic force to ensure that a current is maintained there. And that's really where this energy comes from, is that you can't just kick it and let it go at a constant speed. There will automatically be a force that tries to oppose that motion. And so you're going to have to maintain a push on that in order to get that to go. Now we've worked out, what the force is on a current carrying wire. It's it was ILB, right? ILB, because it's QVB, and then we made the substitution and we changed the Q and the V to an L and an I for current. So we get, and then we substitute what our values for current is. Current is this thing we got back here. It's VLB over R. So that gives us 2 factors of L and 2 factors of B. Okay, again, what I did here is the force is ILB. And then I from the previous example was VLB over R, and that's times another LB, and that's how we get this expression right here. That's the pulling force. So that's kind of a crazy expression there because it involves a length squared and a magnetic field squared. It's awfully strange. And then if you remember back to 110, which you probably don't, there we had 2 expressions for how to talk about power in physical processes, and one is change in energy over change in time. However, there's another one you can have that is the force times a constant velocity times a constant velocity. So if you are pushing something and something pushes back with an equal force, but you're able to, as a result of that, allow the speed to be maintained, then you end up with this really wild expression here, which tells you the amount of power dissipated by the resistance in the circuit. So this is basically how much electrical energy you can generate through this process here. Okay. Now, in this example, we're doing sort of the opposite effect here. In this case, we are going to push this thing to the left instead of the right. If we push it to the left, then positive charge builds up on the bottom. Negative charge builds on the top. That's going to make the current flow in a clockwise direction. Everything else is the same power, all that stuff. But this is just indicating how we can reverse the direction of the current. Okay. What you're seeing here is the basics behind generators, where physical energy, mechanical energy, is converted to electrical energy in a manner like this. But anything that takes mechanical energy, I mean, I guess you could say chemical energy can be converted to mechanical energy, like in a standard motor, and that generates electrical energy. That's a generator. So this is a crude generator, actually. And if you were to take this rod here, if you were to oscillate it back and forth, then you're switching the current on and off and on and off, which is the basics for AC circuits. That's alternating current. Except you can't really fiddle with that thing with the kind of frequencies required for most AC applications. I mean, can you wiggle that thing back and forth to 60 times per second? It's quite the skill. I don't think you can do it. Okay. So, question for you here. An induced current flows clockwise as the metal bar is pushed to the right. Which direction of the magnetic field would do this? Well, bless your hearts. It is into the screen. Let's double check that. velocity's to the right. My fingers point to the right. My palm will open into the page for the into the screen or into the page, whatever you want to say. Thumb points upward. That means the positive charges are building up right here. The negatives are down here, and that causes the current to go in this clockwise direction. Very nice. Let's do a problem. We have a 4 centimeter long slide wire. I guess that's this thing right here, the gray thing. Moves outward with the speed of 100 meters per second. My goodness, slow that down in a 1 Tesla magnetic field. Okay, this is a little ridiculous. Just to let you know, and this is important that it's ridiculous. 100 meters per second is kind of just, what is that? That's ridiculous. It's like 220 miles per hour, isn't it? 220 miles per hour. 224. Wow. 1 Tesla magnetic field, that's insane. That's totally madness. Okay, as at the instant the current forms a loop, at the instant the current forms the loop is a, I can't sentence here. At the instant the current forms, comma, comma. At the instant the current forms, comma, the loop is a 4 by 4 centimeter square with a resistance of 0.01 ohms on each side. We want to find the induced EMF, find the induced current, and find the potential difference to the two ends of the moving wire. Easy peasy, let's do it. All right, so in this setup, this is our square, rectangular, U-shaped, however you want to say it, wire. Velocity is being pushed through. We already know what these things are. There's nothing really new here in terms of what we've just describing so far. Just to be sure about this, the velocity is to the left, magnetic field's into the page, positive on top, negative on the bottom, current is counterclockwise. We're all good here. All right, the induced EMF is V times L times B. Do we have V? Yeah. Do you got B? Yeah. Do we have L? Yeah. And then the current is going to be that divided by R. So let's work out what the EMF is. 100 meters per second times 4 centimeters long times a magnetic field of 1 gives you 4 volts. 4 puny volts. That's like between 2 and 3, AA batteries. Okay. Do you have a 1? If you have a 1 Tesla magnetic field and you can move things at 100 meters per second, you don't have a need for batteries anymore. Put it that way. The current here is enormous. Now, you have to consider the total resistance here. So each side produces a 0.01 ohm resistance. So the current is enormous here, but that's not because of the EMF. It's because the resistance is just whatever it is. It's just small. And then, of course, these are all in equal pieces. So you can say each side contributes, 1/4 to the overall potential difference. The whole thing is, 4 going all the way around. But, take out, like what effectively the battery is here. This is wire. And so what's the potential difference between the two ends of the moving wire? That would be 3 volts. 1 volt along the side here, but 3 along the other side. So, 4 volts is what the EMF is here. But realize when the current's being generated, it's going from up here to down here. That's actually 3 volts. Great. That's electromagnetic induction from our traditional methods. That was a very specific situation I gave you. Okay, a very specific situation. The first question you might want to consider there is, what about that situation is absolutely necessary? Do I need to have a U-shaped wire? Does it need to be a rail that slides along at a given speed? I mean, do I even have that set up? Is there other ways to do that? And if you saw my initial examples, I had a lot of various ways we saw how current is generated. Some involve magnets, bar magnets. Some involve actual motion of the wires themselves. So the answer is yes. There's actually a lot of ways to do it. The example I gave you is not how we're going to be typically solving these problems. That was just an illustration based on the things that you already know on how induction can take place. What I want to do now, and for the rest of this lecture, is to go through an entirely different sort of way of thinking about this that allows us to incorporate all possible aspects of this behavior. And it does involve the concept of magnetic flux. Now, fortunately, you've seen electric flux already. And of course, when we did that, everybody mastered it and completely understood in every possible way. So because of that, I'm sure magnetic flux will be as equally pleasant to understand. But it's the same concept, where the definition of flux is going to be how much magnetic field passes through a given area. It is also a dot product, like the electric flux was, A dot B. From a magnitude standpoint, the dot product is AB cosine theta. Remember the theta, it's a little tricky. If you remember, probably don't, maybe you do. But the angle is the angle between the area vector, which points perpendicular to the area, and the magnetic field direction. So there's two angles you can think about here, and you know what I'm going to do to you, right? I'm going to give you the other angle, and you got to figure out, blah, blah. Okay, anyway. So all the ideas from electric flux before all apply here, except something's different. We actually have a unit for magnetic flux. We did not have a unit for the electric flux. We just simply said it was, what the hell did we say it was? Newton meter squared over coulombs, I think is what it is. Here, we have one called the Weber. The Weber, abbreviated WB, okay, is a Tesla meter squared, but we do actually decide to give it its own unit, the Weber. Okay, so same principles apply as always. If the magnetic field passes completely through the area, then you have the full flux, which is going to be the area, which is here would be A times B times the magnetic field. This is at an angle, so you're going to want to take the angle between the magnetic field and the normal vector. Okay, so A, B cosine theta. Effectively, what you're saying is you're looking, that cosine theta is looking at a thinner cross section. That's the way you should interpret that. And of course, the magnetic field runs along with the area. Then the two are perpendicular, and there's no flux. Okay, again, no big surprises. You've all seen this before. All right, so a uniform 0.035 Tesla magnetic field passes through an 8-centimeter diameter. Here we go again. As shown in the figure, what is the magnetic flux through the loop? So what they're showing here is we have a ring, basically. Okay, a ring that defines a circular area. The angle of the magnetic field with respect to the angle of the loop is 30 degrees, but we don't want that one, right? We don't want that one. We want the angle between the normal vector and the magnetic field, so it would be the complement, or 60 degrees. It is a loop, so we do want to express the area of a circle, pi r squared. So change it to meters and make it the radius 0.04. Don't be one of those garbage people that just doesn't want to use radii or meters. Be a good person and do that. I mean, you can do whatever you want, I guess. Times the magnetic field times the cosine 60, we get 8.8 times 10 to the minus 5 Weber. Let's talk about different kinds of fluxes through here, though. Question for you. Which loop has a larger magnetic flux through it? The intention with this figure here is to show you that the field is either stronger or weaker by the density of the dots here. And you notice that every intermediate dot is removed. So I bet you know what that means. Well, everybody's coming up with B. Is anybody really paying attention to me? That's crazy. Well, thanks. Appreciate that. All these B's. I'm so proud of you. You bet. Because the field is twice as strong, but the area is a bigger factor. It's always a bigger factor. Greater area is going to play more of a role here. So there's more magnetic flux, even though the field is weaker. Even though the field is weaker. All right. Fantastic. The metal loop is being pulled through a uniform magnetic field. Is the magnetic flux through the loop changing in any way? It's not changing. You're right about that. Now, actually, I have another question for you here. Not this question, though. Is there a current in here? Would there be a current in here? What do you think? Yes or no? Would there be a current flying around this thing? Going like this or like this? One of those? Can you do that at the same time? It's hard to change that at the same time. Nope. The answer is no. No, 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 and no. Now, let's talk about this, first of all. One of the things you're about to learn is that change in magnetic fluxes, that's good stuff. We're going to get some electromagnetic induction. But if we don't have change in magnetic flux, we don't. What happens here? Well, velocity to the right, palm opens outward toward me. Okay, so I got to do this. Velocity this way, palm towards me. This hurts my wrist a little. Force is down. So positive charge builds up down here, and negative charge builds up on the top. And that's it. And that's it. No current. No current. What's the difference? What's the difference between the two situations? In the two situations, one of the sides is moving. And in this situation, everything is moving. So there's a big difference there. When only one side moves, only one side gets the potential difference on it. The whole thing gets potential difference on it here. So you do create a potential difference, and you do have positive charge build up in the bottom and negative charge build up in the top. So you've created a potential difference, but you have not created a current here. What about this example? I have a loop. Okay, we're going to have it spin. Okay, is the magnetic flux through the loop changing? You bet it's A. You bet it's A. In fact, well, this is a good illustration of how the way I introduced this topic, it would be very challenging to understand how a current's generated here. Because you could definitely create a potential difference here, and you actually do create a current in the wire here. A current is created here. But it's very complicated to apply those old ideas. That's why we're going to develop these new ideas. Okay, here it is, people. This is going to be your favorite law of all of physics. There's two reasons why it will be your favorite law. One, because it doesn't involve any numbers at all. There are no numbers. All concept. All concept. Whew. Okay, so, of course, I'm being sarcastic. Students do not like this law. It's very confusing for them. Here's what Lenz's Law is. Now, the whole concept, let me set it up first. The whole concept of electromagnetic induction, okay, has two laws that govern it. One of the laws, which is Lenz's Law, involves the direction of current that is induced in all the various situations we can imagine it. The second part is the magnitude of the current, which is what's called Faraday's Law, and we will tackle Faraday's Law on Wednesday. But the rest of today's lecture is on Lenz's Law. So let me read it to you. Let me give you an example, and then we're going to go over a million examples until the end here. Okay, so there is an induced current in a closed conducting loop if and only if the magnetic flux through the loop changes. The direction of the current is such that the induced magnetic field opposes the change in the flux. So what are all the things there that we need to know? You need to have a closed loop of some kind. You need to have that loop be in a magnetic field. So therefore there's a magnetic flux, and that magnetic flux needs to change. The current that is made will attempt to cancel out the change. Anyway, this is the explanation that I like down here. The key to this is the direction of the induced current is such that the magnetic field is opposed. Now, let's see what's going on here. This requires you to do three things. Three things. Okay. Three things. Number one, which direction is the magnetic field? Which direction is the external magnetic field? It is downward. That's step one. Is the field increasing or decreasing? It's increasing because we're pushing this thing down. So we want to cancel that out. If there's a downward and increasing magnetic flux, we want to produce a magnetic flux, a magnetic field, I should say, but flux as well, that is upward. That is upward, because that is attempting to oppose the increase in the flux. How do you make an induced field that's upward? You do that with according to the figure, the way I'm looking at the figure, it would be a counterclockwise current that would produce an upward magnetic field. That's an upward magnetic flux attempting to oppose the change that's occurring here. So the three steps for this particular example was the external field is down, it's increasing. That's step one. Step two, I want to create an upward magnetic field to oppose it. That's step two. Step three is I need a counterclockwise current to produce that upward field. I'm going to do that again about 10 more times before we're finished here. So if you didn't get it the first time, hopefully you get it on the 7th time, or maybe the 8th time, or maybe the 2nd time. I don't know. All right. Here's the steps right here. The flux through the loop increases downward as the magnetic field approaches. Great. The loop needs to generate an upward pointing magnetic field to oppose the change. That was step two. By the right-hand rule, a counterclockwise current is needed to induce an upward pointing magnetic field. What if I pull the magnet out? What's going to happen? Well, the opposite stuff's going to happen. Let's go through it. Now, again, you're going to, every time you do these, step one, step two, step three, you can't get it wrong like this. All right, if you move the magnet upward, the magnetic field is downward, and it is decreasing. So we want to produce an induced field that is also downward because we don't want to see that magnetic flux go away. We want to keep it around. We're trying to oppose the change. So a clockwise current is going to allow a magnetic field to go downward to oppose the change. And so the opposite effect the opposite cause here is producing an opposite effect. Makes sense, right? Question for you here. The bar magnet is pushed towards the center of a wire loop, which is true. Oh my God. Oh my goodness. You guys made my half an hour. You guys absolutely made my half an hour here. All right, it is A. Here are the steps. Step one, external field is upward, and it is increasing. Step two, we want to impose the increase. We want an induced field that's down. Step three, right-handed rule means a counterclockwise current produces a downward field. 1, 2, 3. 1, 2, 3. The bar magnet is pushed towards the center of a wire loop, which is true. Think about this. Letter in the chat. C. It is C. There's no change in flux. As you push this up, the field isn't really getting stronger or weaker or anything because, again, what's happening here is you're looping into S and out of N, and any line that goes through, and so there's no ultimate change here Having this horizontal like this is not an increase or decrease or anything. So, okay. Now, this is my least favorite slide, okay? In all of my physics lectures, okay, I have 4 sets of lectures for 4 different physics classes I teach. And this is my least favorite slide. Okay, because I don't want you to use this as like a little cheat sheet, a little guide to help you figure out the direction of the currents here. This gives you basically every possible situation. Okay, the left-hand side is that there's no change in the field. Nothing happens. Okay, the middle thing here is that the field increases, there's up and down, and then the other one is decreasing, up and down. So it's true, in a way, you could say there are 6 different scenarios. I do not want you, however, to just always refer to this figure as a means to understand which direction of the current is based on how the facts line up. Oh, in this problem, I got a downward magnetic field that's increasing, so you start reading this chart here and you're like, okay, my current's counterclockwise. That would be an extremely bad idea, and it's not why I've included this slide. The reason why I included this slide is because I would like you to go through each of the examples here and understand why the current is these directions here. Okay, notice that it's broken up into 3 steps, 3 steps, 3 steps, 3 steps. So you should look at this in order to help you learn how Lenz's law works, not so that you just use this as a cheat sheet thing. Okay, because you're not going to learn this stuff that way. Okay, it's not a good way to teach it, not a good way to learn it, not good for anything. And I've always toyed with, I should just remove this slide, but then I can't, rant like I'm doing for several minutes and not get back to the lecture. I don't know what I would do for these several minutes, so I don't do that. That's all. But definitely go through these and understand why the currents are the way they are. All right, now I'm going to throw a few curveball type stuff here, see if you can still get what's happening here. We got a current wire. The current's going up. We have a loop out to the right-hand side here. What's going to happen? If you said A, good job. All right. So step 1, which direction is the external field? The current goes up in the wire. So my thumb goes up, and then on the right-hand side, I go into the page. So that's step 1. Into the page. Now the current is decreasing, so it's into the page, and the magnetic field is decreasing. Okay? Now to oppose that, we're going to have to create a magnetic field that is also into the page, because we don't want to see it go away. We want to see it stick around. So we're going to have a field that goes with it. And that means, according to the right-handed rule, I stick my thumb into the page, and this means I get a clockwise current out of it. Fantastic. Okay. So now, flux is into the screen and decreasing. Step 1, and then if you're like, okay, I got step 1, let me go back and look at this little thing here. And then if you do that, hopefully in your mind you will remember my words and say, oh, my government said I shouldn't do this. Oh, I feel so bad. Okay, I'll learn it. The magnetic field is confined to the region inside the dashed lines. As you can see here, it is 0 outside. The metal loop is being pulled out of the magnetic field, which is true. Again, think about this now in terms of the ideas of flux, not the way we described it earlier. It's not easy to think about that stuff. Because imagine some of these situations we have here. I mean, how exactly would you, with those other methods? I mean, it would be impossible because these are some things you don't know yet. Okay, what do you think? Oh gosh, ABs. Okay, so you have to ask yourself this question. Is the magnetic flux increasing or decreasing? It is decreasing. Into the page and decreasing. We don't want to see it decrease. We want to have an induced field that goes into the page, and that means a clockwise current is needed to make a field go into the page there. Now you will be producing a magnetic flux that is throughout the loop. We're only really interested in what's going on in the portion that's still in the field though. But having the motion go to the left here is a decrease in magnetic flux. Now if you actually go back to the examples at the very beginning of the lecture here, and you think about things in terms of flux, when you slide that thing around, you can see why the currents are the way they are. If you slide it to the right, you're increasing the magnetic flux. If you slide it to the left, you're decreasing the magnetic flux. Okay, I have one more question for you. All right. Don't put a letter in because we're done here basically. So I just want to get through this and then you guys can take off. Immediately after the switch is closed, the lower loop exerts blank on the upper loop. Okay, let's talk about it. So you can see from the battery here, this is going to produce a current that is, right, counterclockwise. So that's going to produce an upward magnetic flux. And if we're talking about it, after the switch is closed, then that's going to produce a increase in magnetic field. Why is there 6 steps here? Oh, it's because I'm asking about forces. Okay, so the battery drives a counterclockwise current. Okay, increases rapidly, so it's a magnetic field that's up and increasing. There's going to be a field up here that's induced that's going to want a magnetic flux to go downward to oppose the increase. So it's going to have a opposite clockwise current. And when you think about the direction of the fields, you have to also remember the dipole directions here. The bottom one, because it's counterclockwise, is north, up, south, down. This is clockwise, so that's down for north and up for south. That's opposing fields. They're going to want to be pushed apart from each other. It's like having 2 magnets and try to put the polarities together. It's going to require a repulsive force. Now, this is the last slide here. However, this involves so much. This one question really incorporates the vast majority of what we did today and actually starts to incorporate some ideas earlier about magnetic forces. So